Welcome to EduTatva Career Info Series. Today, we're diving into a brand new explainer, and we are completely demystifying the reality of a biotechnology engineering degree. We're going to break down exactly what this highly progressive field is all about, taking it from the microscopic world of tiny cellular subsystems right up to massive industrial scale manufacturing. Okay, let's dive into this. The entire field really hinges on one massive core industry question. How do we take a microscopic genetic breakthrough, something that happens in a tiny petri dish, and manufacture it safely by the metric ton? That is the fundamental challenge, right there. It's exactly what separates this engineering discipline from your traditional biological sciences. And this brilliantly illustrates the difference in career trajectories. So think about a traditional BSc or MSc in biotechnology. That route is heavily focused on pure laboratory research and microdiscovery. Basically, you're the one discovering things in that petri dish. But a BE or B.Tech in biotechnology engineering, that is all about scaling up. You are the person taking those fragile discoveries and figuring out how on earth to manufacture them safely by the metric ton for real-world commercial and therapeutic use. Here's our quick roadmap for today's explainer. 1. An intro to biotech engineering. 2. The 4-year curriculum. 3. Career profiles and sectors. 4. R&D versus the factory floor. And 5. Psychometric fit and risks. Let's jump right into Section 1, Intro to Biotech Engineering. So to actually pursue a bachelor's degree here, you need a seriously solid scientific base. We're typically talking a 10+2 with physics, chemistry, and mathematics. Now, because you are dealing with living matter, obviously having biology is highly advantageous. But if you're coming from a pure math background, honestly, don't panic. Many engineering universities actually offer specialized biology bridge courses to get you caught up. You'll master organic chemistry, analytical calculus, and biochemical thermodynamics, and you'll usually enter the field through central scientific pipelines like JEE Main or KCET. Moving right along to Section 2, the 4-year curriculum. Let's see how this builds. Your 4 years in college transition very systematically. Step 1 covers your foundation years. That's semesters 1 through 4. Here, you're really grounding yourself in classical engineering principles, things like fluid mechanics, right alongside cell biology and thermodynamics. Then, in Step 2, you jump into the core specializations for your last 4 semesters. This is where it gets incredibly cool. You get to the heavy-hitting sci-fi reality of the job. We're talking using recombinant DNA technology like CRISPR, designing massive industrial bioprocess operations, and parsing gigantic genomic sequences in bioinformatics. All right, Section 3, Career Profiles and Sectors. Now, what's really interesting about this slide is the sheer diversity of the global industries that are actually hiring you. In biopharmaceuticals, for instance, you might literally be manufacturing insulin or vaccines. Over in agricultural biotech, you're engineering pest-resistant crops. Or you could work in industrial enzymes, synthesizing green chemical alternatives. Or even environmental biotech, where you're deploying an army of microbes to eat up an oil spill. The applications are absolutely massive. And within those sectors, you have incredibly specialized paths you can take. A bioprocess or fermentation engineer is out there on the floor physically optimizing massive industrial bioreactors. On the flip side, a bioinformatics analyst operates entirely in the digital realm, using complex computational models to mine genomic data. You've also got downstream processing engineers scaling up purification, genetic engineers designing synthetic DNA, and quality control and QA analysts who make absolutely sure that every single batch strictly complies with health standards. Next up, Section 4. We're looking at R&D versus the factory floor. There's a really fascinating split in your daily work environment within this field. So molecular and genetic R&D operates in a microscopic, clean room regime. The focus there is all on sequences, data, and logic, and the tangible output is a verified, novel plasmid blueprint. Now, contrast that with bioprocess operations. That side is macromechanical. It's industrial. They're focusing on physical vessels, thermodynamics, and high yields. Their tangible output isn't a microscopic blueprint. It's literally a 10,000-liter batch of purified pharmaceutical-grade insulin. And finally, Section 5, Psychometric Fit and Risks. Are you a spontaneous rule breaker or a meticulous systems thinker? Let's find out. Let's get a bit personal here. According to vocational psychology, the ideal Holland code for this field is ICR or ICE. Investigative is your core engine, probing the micro world and testing hypotheses. Conventional is also immense here. In highly regulated labs, strict adherence to standard operating procedures is absolutely critical for avoiding million-dollar contamination disasters. And finally, realistic involves handling complex hardware, while the enterprising trait really drives the engineers who are commercializing those corporate supply chains. So the crucial point is how this actually translates to personality types. The INTP logician is a totally natural fit for molecular research and abstract biochemical relationships. Then you have the ISTJ logistician, who excels in downstream processing and plant management. Why? Because of their deep respect for established rules and exceptional attention to microdetails. And of course, the INTJ systems architect is exceptional at designing the structural layouts for complete biomanufacturing plants. But we definitely have to look at the risks too. The ideal fit is meticulous, rule-abiding, and comfortable with really slow biological timelines. But if you're a dynamic action seeker or a creative rule breaker, caution is definitely advised. Highly spontaneous or artistic profiles face what we call velocity friction, basically getting frustrated with the slow pace of cell cultivation. And even more importantly, they face contamination friction. In this field, deciding to deviate from a validated protocol just on a creative whim, that doesn't result in a masterpiece. It ruins a million-dollar batch. Ambiguity here is a massive liability. So the big question is, do you have the meticulous patience to map the microworld and the engineering ambition to scale it up to change the macro world? The future of human health and global sustainability might just depend on it. Follow us for more. For psychometric-based career counseling, contact us.